Okay, so now what I want to do is I want to talk about the Fourier transform. We're going to do both discrete time and continuous time, but we're going to do the continuous time first because it's something that you're familiar with. And just like in the case of the other things we've looked at in terms of the transforming between time and frequency, we're going to have something that tells us how to take a signal and get from it this representation in the frequency domain. That's going to be our analysis equation. And we're going to get something that tells us how to take the frequency domain description and go back to the time domain. So that's the thing that I was referring to when we have a frequency response of a filter. That's the frequency domain description. We would like ultimately to go back and say, what's the impulse response, the time domain characterization. So in the case of the Fourier transform, I'll just write, usually we write the synthesis equation first, even though sometimes logically we actually get to the description of the transform by developing the analysis equation. So the synthesis equation tells us how to get the signal from its transform. So I haven't told you yet what that transform is, but I'm going to show you how to get the signal back. It's going to kind of resemble what we've seen in the other cases. We're going to take this transform is going to be a function of omega, and it's going to be actually in the form of x of j omega, just like the frequency response of our filters. In fact, the frequency response of a filter is going to be, in some sense, the first case of the Fourier transform that we've run into in this course. And then we have to take this thing and use it to somehow combine all these values at different frequencies. So we have to kind of sum up over the frequencies, which in this case, because it's a function of a continuous spectrum of frequencies, we have to take an integral. So we integrate over omega, and the thing to keep in mind is if you want to kind of compare this to when we had a periodic signal, remember there what we had was, this was a periodic signal with fundamental frequency omega naught. So actually it only contained frequencies, so to speak. It only had frequency content at multiples of omega naught, and there we summed up over all of those harmonics, all of those k omega naught frequencies. Well, here it's not periodic. This was for periodic. Now we're dealing, this is for, in some sense, an arbitrary signal. So you can see the analogy. This is the guy that's replacing the Fourier series coefficients. It's a continuous function of frequency because this thing might have not just multiples of some fundamental frequency because it may not be periodic. Then we have the analysis equation, which tells us what this mysterious x of j omega is. And actually the formula is going to look very familiar to you because it's exactly the same formula that we used to define the frequency response of a filter. So remember there, what we did is we took the impulse response, so the general version of that h of t now is going to be this general signal x of t, and we multiplied by e to the minus j omega t and integrated with respect to time to give us a function of omega. So this is actually, if I plugged in h of t and h of j omega, that would be exactly what we decided was the frequency response of our system. It was the thing that came out of the eigenfunction analysis. So this is the general form, and you can recall when we compare it to the periodic signal, there what we computed the equivalent of this frequency domain representation was these Fourier series coefficients. And there we had to take a sum, an integral over one period of x of t e to the minus j k omega naught t. dt. Okay, so you can see kind of the analogy. In this case, it was an infinite sum. It becomes here an integral. Here it was an integral over one interval. Here it's an integral over the whole time domain. But the general structure is the same. It's the signal multiplied by e to the minus j of frequency times t. E to the minus j omega t, and you integrate over t. Okay, so that's the Fourier transform. And in fact, what I want to remind you of, I think you probably did this in 45, is how we actually get these expressions essentially from these expressions. So what we typically do to kind of motivate the derivation of the Fourier transform as a way of describing a signal in the frequency domain is we assume that we have a signal. We usually say x of t is not periodic, because if it was periodic, we would just use the Fourier series. So we're assuming it's not periodic, it's aperiodic. And for the purposes of this kind of heuristic motivation, when I say heuristic, it's actually precise in the case where the signal is finite duration. So a little more work is needed in other cases. So what's an example of a finite duration signal? Well, it might be something that comes along and then goes up. It can do anything it wants, but it's finite duration. It eventually comes back to 0. So that would be an example of a finite duration signal. Another example would be a square pulse. Just a perfect square pulse. That would be another example of a kind of finite duration signal that we'll be interested in. So for the case of a finite duration signal, we can give an analysis. I'm not going to go through necessarily in great detail the derivation. I'll show it to you, but I'm not going to repeat it in great detail. We can get it by looking at the periodic case, and the way we do it is we use this guy to build a periodic signal. We just take this and then we repeat it. We say, okay, we're going to take this finite duration shape, and we're just going to repeat it every integer multiple of capital T. That gives us a periodic signal, and now we can figure out the Fourier series. And then you say, well, what good does that do us? That's not this signal, that's a periodic version. Well, then what we do is we say, okay, now let's let the period go to infinity. Let's push those copies all the way off until they're out of the picture. And once they're out of the picture, we're just left with the finite duration signal. So we see what happens in the limit when we evaluate the Fourier series. So here's the idea described in terms of this square pulse, or rectangular pulse, I should say. So it's going to be something that is magnitude 1, amplitude 1, from minus T1 up to T1. And now we can say, let's remember what the Fourier series was when I repeated this every capital T. So now imagine in your minds that I've now kind of repeated this thing. I've created a new signal built out of this, which repeats every T. So if this guy, original guy, let me actually just draw it up above my original x of t. Here was my original x of t, just this square pulse. And now I'm creating this periodic signal. Let me call it like x tilde with a subscript capital T, so that I know I've made it periodic with period capital T. Well, for this guy, we compute the Fourier series. And that's where we got something that looked like a sinc function. Except it was a sinc function that we sort of only evaluated at because we know that the Fourier series coefficients are indexed by k, and those have to do with precisely those harmonics, k times the fundamental frequency. So omega naught is going to be 2 pi over, in this case, will be 2 pi over t. So it's going to be at harmonics of that. And now what we say is, okay, given that, let's play a little trick here. let's look at this expression and say, well, we just evaluate, there's a kind of a common form to this. In fact, the Fourier series coefficient at the kth harmonic, at k omega naught, is what I get if I take this function right here. This is now a function of continuous frequency, 2 sine omega t1 divided by omega. I just evaluate that at the harmonic, at k omega naught. Now, then I have to worry about this capital T over here, so I'm actually going to move the T over to here. So we normalize the Fourier series coefficient by multiplying by the period, and suddenly they all have exactly the same form. They all look like something that we get by evaluating this continuous function of frequency omega at the harmonics. And so what we do is we give a name to this continuous function of frequency, which is like the envelope signal, right? It's going to be this continuous function, and then we just pick out certain points, the values at the harmonics, and that gives us the normalized Fourier series coefficients. We call that x of j omega, 2 sine omega t1 over omega. And here's the picture. This is where I repeated that signal every capital T. And the Fourier series coefficients, of course, we index them by k, the Fourier series coefficients, but we can associate with each one of those indexes the associated harmonic. So 1 would be the first harmonic omega naught, 2 would be the coefficient that belongs to the second harmonic 2 omega naught. And the picture basically looks like this. Here's my sinc function, sine of omega t1 over omega. So it's going to be a decaying ripples. And then these are the values of the normalized coefficients. Now, what happens when I let t increase? Well, when I let t increase, what's going to happen is that, remember, if we think in terms of plotting it as a function of omega, so associate to the indexes the actual frequencies, what happens as t increases, as the frequency spacing between them, which is basically omega naught, 2 pi over capital T, is going to get smaller and smaller and smaller. The envelope curve stays the same. It's always 2 sine omega t1 over omega. So what happens is, as you increase that frequency, you increase that frequency, those samples of this envelope curve get closer and closer together. Because the new omega naught, the new frequency, 2 pi over t prime, omega naught prime, is going to be smaller. Now, if you let t go to infinity, that omega naught, that new fundamental frequency, goes to 0. These guys basically, fill up the whole picture. And what you're left with is precisely that envelope curve, 2 sine omega t1 over omega. That's the Fourier transform of the isolated pulse, of the isolated rectangular pulse. It's that function. So you can see it's just kind of a limiting operation derived from the Fourier series. So this just kind of goes into the details. I encourage you to look at the derivation. It's just a matter of verifying that you get these Fourier series coefficients and represent them as evaluations of this magic formula, x of j omega. What was x of j omega? Well, it turns out that when we look at the formula for the Fourier series, we want it to be this. Because remember, the Fourier series was x of the a sub k, so the value at k omega naught was x of t e to the minus jk omega naught t. We integrate that over one period, but you can see that when you do this calculation, we can essentially view that integral as being from minus infinity to infinity. And then you just kind of go through the substitution of the formula in the synthesis equation, and you magically come out with this formula right here. So x of t is 1 over 2 pi integral of x of j omega e to the j omega t d omega, where x of j omega was defined by this. Okay. So it all falls out of really looking at the synthesis and analysis equations for the Fourier series. And so that's the upshot. That's what we end up with for the definition of the transform. So I've put the analysis equation first here, because that kind of comes out of looking at that envelope signal in frequency domain. And then this is what you get out of looking at the synthesis equation. Okay, so you can see it really kind of derives from what we've done already. And as I said, we've actually seen an example of it. If we let h of t be the impulse response of a continuous time LTI system, if we plug into that formula for the Fourier transform, we get exactly the thing that we called the frequency response that came out of looking at the eigenfunction property. That came out of the convolution property of the LTI system. And so we write it, generally we write x of t with its Fourier transform x of j omega. So in this case, it's h of t with its Fourier transform now, the frequency response, h of j omega. So just as with the Fourier series in continuous time, we have these annoying convergence issues, because when we do remember we had some problems. We didn't really have a problem with the analysis equation. We did have a little bit of a problem with the synthesis equation. In other words, we said if we take a periodic signal that's well behaved and plug it into here, like if it's finite energy, so if the integral of magnitude of x squared over one period is finite, we can evaluate this and we can get the a sub k's. If we plug them into here, what we'd like to say is that this infinite series evaluated when we plug in a particular value of t is going to actually give us x of t. And what we saw is that it's not quite that simple. We saw that if the signal had finite energy, then this summation sort of was close to x of t in the sense that it converged in terms of energy. So the sum of the magnitude squared of the difference between the summation as you let the limits go to infinity and the signal would go to zero. So that was convergence in energy, and it just required that the signal be finite energy. Well, we have a similar thing here, except now the signal has to have finite energy not over a period, because it may not be periodic. And in fact, the derivation I gave here was for really a finite duration signal, but actually it applies to other signals that aren't finite duration, such as, for example, one-sided exponentials that go off to infinity, or even two-sided exponentials that go off to infinity in both directions, or things that kind of look like a big pulse that goes to zero. So there are a lot of signals that aren't finite duration that all of these results will apply to as well. What we do require, in this case, is that when you integrate the magnitude of the signal squared over the whole range, t equals minus infinity to infinity, it's got to be finite. So that, for example, would apply to like a decaying exponential in both directions. It would not apply to some signal that does weird things and then heads off to infinity, on the right and left. We'll run into some signals like that later. So it wouldn't apply to increasing exponentials. But for things like decreasing exponentials, this is going to be okay. For those types of signals, then in fact, we can evaluate the Fourier transform. In other words, just like for those signals, we could compute the a sub k's. So we get some finite number. And if we plug that transform into the synthesis equation and take our integral over some increasing range of frequency, like from minus w to w, and let w go to infinity, then the difference between this integral and the signal, which will have the property that its energy goes to zero. So that means we get convergence in energy in the Fourier transform case, provided that our signal satisfies this finite energy condition. So it's completely analogous to the Fourier series case. And similarly, if we now think about our signal as being an impulse response of an LTI system, what it tells us is that if our LTI system satisfies this property, that the energy in the impulse response, So this is now integrating over all time from minus infinity to infinity. If that's finite, then the frequency response is well defined. Then we can talk about the frequency response of that system. Now, just as in the case of Fourier series, you may say, well, I'd like to know more than just convergence in energy, that the energy in that error signal goes to 0. I want it to actually converge to x of t. I want pointwise convergence. I want that sum to converge to the exact value of the signal. Well, Dirichlet strikes again. So there are conditions called the Dirichlet conditions for an aperiodic signal that if they're satisfied, then you'll get pointwise convergence except at points of discontinuity. Again, just like the periodic case. So what are the conditions? Well, they're actually very similar. This one is absolute integrability. So you have to be able to integrate the magnitude of the signal over the entire time span and have that be finite. You can't have more than a finite number of maxima and minima within any finite time interval. So that's very similar to the periodic case where we didn't want something that was oscillating crazily and had an infinite number of maxima and minima. And you also want a finite number of discontinuities, but this has to be true within any finite time interval because there's no period here. So if those hold, then x of j omega exists. So you could get an x of j omega by integrating this, and you could then plug it in here. And then what you'll find is that you get pointwise convergence at the points of continuity. And at the points of discontinuity, the value of that integral will be the average of the values on either side. So when we take this signal, this is a perfect example, which is a little bit shocking when you think about it, that I can describe this discontinuous finite rectangular pulse as basically a sum, but it's kind of a sum over an infinite range of frequencies. I can represent it as a sum of these periodic complex exponentials. That's a little bit shocking, right? That you can take a whole bunch of sine waves and add them up. It's actually going to be, we can think of it that way, but we'll represent it here as complex exponentials, these periodic signals. And somehow or other, we end up with a finite duration signal if we give them the right weights. We use them to the right amount and get this thing. And what we'll get is that when we compute that x of j omega, which actually we just computed, it's that sinc function. So it's telling you how much of each frequency to use. You're using less and less of the high frequencies, but you have to use frequencies, all the way out to infinity. You're going to end up getting an integral that converges exactly to 1 here and to 0 here. And at these edges, at the points of discontinuity, it's going to converge to exactly a half.